All right, we're continuing on with worksheet 2, quantitative energy problems part 1. Yesterday, I talked to you about how to sketch a warming or cooling curve, how to decide which equations to use, and then I told you to go ahead and round to 3 sig figs. I walked you through your equation bank. Anytime there's a temperature change, we're going to use Q equals mc delta T. Anytime there's a phase change, we're going to use Q equals the mass times the heat of fusion, or Q equals the mass times the heat of vaporization. And the heat of fusion is for freezing, melting. The heat of vaporization is freezing, condensing. This is always going to be in degrees Celsius, so don't do Kelvin. We're not dealing with gas systems. And then for H2O, here is all of the reference data for the heat of fusion, the heat of vaporization, and the heat capacity for solid water and liquid water. I also walked through the fact that this is our strategy. We're going to start off by using the problem to sketch a temperature versus time graph, or heating curve. Then we're going to determine how many parts there are to the graph and assign equations to each. Then we'll list what the word problem gives us and what we know from the equation bank, and finally we're going to substitute and solve. Okay, so there's our strategies. Here is number 3. Number 3 says, suppose that during the icy hot lab that we have 6,500 joules of energy being transferred to 450 grams of water at 20 degrees Celsius. We want to know the final temperature. Cool. I see that we are starting, says we're at 20 degrees, and we want to know final temperature. And we are transferring into water. So I'm going to start at 20 degrees Celsius, and I know that 20 is nowhere near my 0 or my 100. So I'm going to assume that transferring 6,500 joules of energy is going to just increase my temperature to some question mark. Okay? So if I look at this, the only equation that I'm dealing with, since I have a temperature change, is Q equals mc delta T. Great. What do I know? I know that there is 6,500 joules of energy. That's our Q. Q equals 6,500 joules. We have 450 grams of water. That's an M. We know that the starting temperature is 20 degrees Celsius, and we need to know that. The other thing I know is we're at liquid water. So my C of liquid water is 4.18 joules per grams degrees Celsius. And I'm going to add something here simply because this is what we're solving for. We know that delta T is going to be T final minus 20 degrees Celsius. Okay? So in essence, what we want to know is what is this delta T? Because then I can use this delta T to figure out my final temperature. So let's go ahead and set this up and solve for delta T. Okay, so 6,500 joules equals 450 grams times 4.18 joules per gram Celsius times, I'm going to put delta T here, because I'd rather deal with this separately. Okay, I need to solve for delta T. I'm going to go ahead and get rid of my grams here just to get rid of some units. So I'm going to say 6,500 joules equals have 450 times 4.18. 450 times 4.18. 1881. 1881 joules per degree Celsius times delta T. Fantastic. I've simplified this a bit to make it easier on myself. I have 1881 joules per degree Celsius times delta T. I need delta T to be by itself, so I'm going to reverse what's going on here and divide both sides by 1881 joules per degree Celsius divided by 1881 joules per degree Celsius. Now, something divided by itself cancels out. So this cancels out of the side with degrees delta T, which is great, that's what we want. And over here, before I put this into my calculator, I see that I have joules divided by joules over degrees Celsius. My joules are gonna cancel out. I'll be left with degrees Celsius, which is fantastic, that's what I want. So, I'm gonna put into my calculator, C500 divided by 1881. I get 3.456. We'll do that. So my change in temperature is a positive 3.456 degrees Celsius. Fantastic. Now I can take this and put it here. Delta T equals TF, my final temperature, minus 20 degrees Celsius, my starting temperature. And I learned over here that 3.456 degrees Celsius equals T final minus 20 degrees Celsius. I'm going to add, because this is subtracting here, plus 20 degrees Celsius, and I get that my final temperature is 23.456 degrees Celsius, and I want that to be in 3 sig figs, which is 23.5 degrees Celsius is my final temperature. Okay, let's go ahead and solve number 5. So I have a bag full of ice at 450 degrees, or 450 grams at 0, sits on the counter and begins to melt to liquid water. How much energy must be absorbed by the ice if 2/3 of the mass is melted? All right. So we're going to do our step 1 is always going to be sketch a temperature time graph. So this is temp, this is time, and I see that I'm starting at 0, and we're going to melt. Cool. So next step is determine my equations. Here I have melting, so I'm going to use Q equals M times HF. Now I'm going to make a list of what I know based on the problem. I know my mass is 450. However, note this part here. I only want to melt 2/3 of the mass. So I need to know what 2/3 of this is. So I'm going to times this by 2/3. Okay. I need to make this into scientific calculator. Okay. So I want 450 times 2/3. equals 300. So the mass I want to use for this is going to be 300 grams. Okay, what else do I know? Well, I know that T initial is 0. However, we're just melting, so I kind of don't need to know that. And I want to know energy. I have mass. I want to know energy. I also have heat of fusion because it's right here. So my heat of fusion is going to be 334 joules per gram. Cool. I've kind of written all the things I want to know. Now I can substitute and solve for the unknown. So I get Q is equal to mass times HF. So Q is going to be equal to 300 grams times 334 joules for every gram. My grams cancel out, and I'm going to put this into my calculator. Here's my 300 times 334. I get 100,200. Joules. Now I only want this to be 3 sig figs, and this is in my 3rd sig fig position, and next door is a 2. So I'd be tempted to go 100,000. But if you remember with our rules for sig figs, there's no decimal place here, which means this only has 1 sig fig. So this is one of those cases where using scientific notation is appropriate. So for scientific notation, I have an imaginary decimal here, and I move it over 1, 2, 3, 4, 5. And I'm going to put 0, 0 here to show that these zeros are significant. And I moved it to the 5th position. There we go. 1.00 times 10 to the 5th joules of energy must have been absorbed by the ice. All right, go ahead and work the rest of the problems between 1, 2, 3, and 5. That kind of shows you all the different variations that you could encounter. Good luck.